this lecture in the Build DeepSeek from Scratch series. Today, we are going to start understanding the quantization methods which DeepSeek actually implemented in their version 3 report. So, if you look at the DeepSeek version 3 technical report PDF, they have a section called FP8 training or floating point 8 training, and in this section they implemented several aspects with respect to quantization, and I've divided those into five major aspects: mixed precision framework, fine grained quantization, increasing accumulation precision, mantissa over exponents, and then online quantization. In today's lecture we'll cover mixed precision framework and fine grained quantization. In the previous lecture, we have had a introductory look at quantization, and some of these concepts will be relevant to you in today's lecture as well. Essentially, the main idea of quantization is that parameters take up space. Every parameter in a large language model takes up space. So, if the parameter is represented as a floating point 32-bit number, it takes up more space than, let's say, if it's represented as floating point 16, etc. So the main aim of quantization is to reduce the precision of a model's parameter from higher bit, let's say from 32-bit to a lower bit, let's say 8-bit or 16-bit. So through this, the main advantage which we get is that we reduce the total memory requirements, but at the same time, we don't pay that much of a heavy price with respect to the accuracy of the model. Of course, the accuracy slightly reduces because now every parameter will be represented in a low precision, but that much reduction in accuracy of the large language model is typically fine for us because it does not degrade the performance that much. In today's lecture, you will come across floating point 32, which consists of 32 bits. Then you will come across floating point 16, which consists of 16 bits. Floating point 16, the range is much reduced compared to floating point 32. You will also come across BF16. So the range of BF16 is same as floating point 32, but its bits are the same as floating point 16. So it still has 16 bits. BF16 is brain float 16. Then there is also integer 8, whose range is very small, minus 127 to 127, and it has 8 bits. One more concept which we'll see when we come to fine grained quantization is that when you want to actually quantize and go from a floating point 32, let's say, to a floating to an integer 8, what you do is that if you have a sequence of numbers in floating point 32, you divide all these numbers with the highest number, in this case 10.8, and then what you will do is that you will multiply it with 127. So keep this in mind that we divide by the highest number and then multiply it with 127 if we want to, let's say, quantize from a floating point 32 to an integer 8. All these concepts which I'm showing you right now, we have covered it in previous lecture, but this quick summary will be enough for you as we get started with today's lecture. So let's get started with the first major concept which DeepSeek implemented, and that's something called as the mixed precision framework. So if you look at the DeepSeek paper, they have the mixed precision framework in section 3.3.1, and they have a schematic which is corresponding to this, which looks like here. Now, based on the introduction which I gave you, you'll already understand FP8, BF16, so this floating point 8, a brain float 16, floating point 32, BF16, etc. But now let me explain to you what this F prop means, what this D grad means, what W grad means, etc. So when you look at a large language model, there are a number of parameters which get multiplied together. The typical operation which happens in a simple neural network layer is as follows. We have y equal to w times x, where x is the input, w are the weights, and y is the output. So a forward pass or a forward propagation, which is referred to as f prop over here, are the operations in which weights are multiplied by inputs. So y equal to w into x. And now I'm going to explain to you how DeepSeek stored the weights, stored the inputs and the output in which quantized format. Okay. So let's first take a look at the inputs. When the inputs were used in this formula, they were converted from a brain float 16 to a floating point 8. Okay. So floating point 8, as you must have seen, it has a much lower range compared to brain float 16, and of course much lower number of bits. So it takes less memory. Weights, on the other hand, are maintained in a high precision, which means they are stored in brain float 16 or floating point 32, but the weights are converted into a floating point 8 on the fly. So when you take this multiplication, you have a floating point 8 weight multiplied by floating point 8 input, which gives me the output. And the output is computed initially in floating point 32, but for numerical stability, it's converted back into brain float 16. So whenever we have forward propagation modules anywhere in the large language model, what DeepSeek did was that they did this multiplication of a floating point 8 and a floating point 8. So it took up less memory, and the output, they computed the output initially in floating point 32. Remember that when a floating point 8 is multiplied by 40 floating point 8, we get a higher decimal representation. So we can get the output in a higher format compared to the inputs. So the output is computed initially in floating point 32 for numerical stability, but then it's converted back and stored in BF16 to optimize the memory. Remember, BF16 has 16 bits and it covers the entire range as floating point 32, which we already saw over here. If you remember, this was the BF16 which we saw. It covers the same range as floating point 32, but it has 16 bits. So it takes up less memory compared to floating point 32. So now you'll be able to understand this f prop block over here, right? If you see, the f prop block has inputs which are floating point 8, weights which are floating point 8, the inputs and the weights are multiplied, and the output is initially computed as floating point 32, but it's stored in memory as BF16 or brain float 16. That's the way to interpret this f prop block. Along with forward propagation, we also have backward propagation. So if you look at a neural network like this, and these are the inputs of a particular real layer, and these are the output. Remember, we are doing backward propagation, right? So when we reach a particular layer, we'll have the partial derivative of the loss with respect to the output of that layer. And then we'll need to find two things. We'll need to find partial derivative of loss with respect to weights, because we'll need to update the weights of this layer, and we'll also need to find the partial derivative of loss with respect to the inputs of the layer. Why do we need to find the partial derivative of loss with respect to inputs dl by dx? Because this dl by dx will serve as the dl by dz of the previous layer. So when you look at a given layer, you will need to find the partial derivative of the loss with respect to the weights and the partial derivative of the loss with respect to the inputs. The partial derivative of loss with respect to inputs is given by this formula dl dx, which is also called as d grad over here. So this d grad is the partial derivative of loss with respect to the inputs, and it's given by the formula dl dz multiplied by the weights transpose. Now to get the partial derivative of these inputs, the weights are again converted on the fly to floating point 8 for this calculation, and dl by dz is stored as brain float 16, but it's converted to floating point 8 for computation. And dl by dx is computed initially as floating point 32, then converted to brain float 16. So if you take a look at this entire computation, dl by dz is on the fly converted to floating point 8, weights are on the fly converted to floating point 8, and the multiplication, it's computed as floating point 32 and stored as bf16 or brain float 16. So this is exactly what you see over here, right? Weights are floating point 8. Weights are multiplied with the output gradient, which is floating point 8. The multiplication is initially computed as floating point 32, but it's stored as brain float 16. That's my input gradient. But I also need the gradient with respect to the weights, right? That's W grad. And W grad is given by this formula, partial or the gradient with respect to the weights is equal to X transpose multiplied by dl dz, and X is stored as floating point 8. dl dz again is converted from brain float 16 to floating point 8. And keep in mind that dl by the partial derivative with respect to the weights is stored as floating point 32 to ensure numerical stability for weight updates. So this is not converted into floating point 8, because this will ultimately lead to my weight updates, right? So if you look at dl by dw, you'll see that the weight gradient, right, which is computed after multiplication of the inputs multiplied with the output gradient, The weight gradient is computed as floating point 32 and it's stored also as floating point 32. It's not stored as floating point 8 or BF16. It's stored in a very higher precision and higher number of bits. So this is stored as floating point 32, as you can see over here. And then we have these weight updates. So this is the optimization state, and the for the optimization, the weights, the initial weights are stored as floating point 32. DL by DW, of course, is stored as floating point 32. So the initial weights minus this DL by DW, that gives me my updated weights, and that's stored as floating point 32, right? So after the weights are updated, the master weights are converted to BF16 for next iteration forward pass, or they are converted into floating point 8 when needed. So these weights, when they are utilized for calculations, they are converted on the fly to floating point 8. But remember that the master weights are computed as floating point 32, and the partial gradient with respect to the weights is computed as floating point 32. So this portion is shown in this part of the schematic over here. We get the weight gradient in floating point 32, and we get the master weights as floating point 32, and they are on the fly converted to floating point 8 to get my forward pass, to get my D grad, etc. Okay, so this is how the different parameters are stored in different quantized formats when we are doing the forward pass and when we are doing the backward pass. Okay, so now I hope that when you look at this figure, you will actually completely understand what's going on. Figure 6. If you directly look at this figure, it's very difficult to understand what's going on. But now, when you look at it, you will understand what the mixed precision framework actually means. And so now, if you compare the advantages of what exactly we are doing here, why do we do this mixed precision, right? So you see, we are converting several variables into floating point 8 on the go. This significantly reduces the computational and memory cost, and it provides us a big speed improvement, uh, especially compared to using BF16. So if you look at this schematic now, there are several variables which are converted to floating point 8 on the fly for calculations during the forward pass as well as during the backward pass. This speeds up the computations by a lot. And GEM means matrix multiplication operations, general matrix multiplication operations. They involve a lot of multiplications like this. So using a floating point 8 significantly speeds up my computations and it reduces my memory cost. But you see, we are smartly also retaining some states in higher precision, right? Master weights and the optimizer states are stored in floating point 32 to ensure training stability. That's why this is called as mixed precision. During computations, some variables which are not as important are converted to floating point 8 on the fly, but variable states which are important, so for example, these master weights, for example, then partial derivative of loss with respect to W, those are maintained as floating point 32. That's why it's called as mixed precision. Now, in the paper, DeepSeek mentioned that embedding modules, output heads, gating modules, normalization, and attention operators are sensitive, and hence these are retained in higher precision. That's an important thing to understand. So, if you take a look at this section which they have mentioned, they mention here clearly that which operations are retained in higher precision. For this reason, after careful investigation, we maintain the original precision for the following components: the embedding module, token and positional embedding, the output head, where the final output head converts from embedding dimension to the dimension of vocabulary size, mixture of experts gating modules, normalization operators, and attention operators. The floating points or the precisions are higher for these operations, either they're BF16 or floating point 32. Whereas, let's say, all the other areas where we have weight products, we have weight multiplications, those are calculated using the floating point 8 format. So you see, we are using low precision, but at the same time, for some calculations, we are using high precision. So we get memory reduction, computational efficiency, and numerical stability at the same time. It's a very smart way for doing operations. Operations which are not important, or we can do fine with reduced precision in those operations. We convert those into floating point 8, whereas operations which are important, those are retained in floating point 32, especially in mixture of expert gating modules and attention operators. embedding modules, etc. All of those are retained in higher precision. So this is the main concept behind understanding mixed precision framework, and that's the first quantization technique which DeepSeek implemented. Along with this, the second quantization technique, which is also shown in their second figure, which they implemented, is something which is called as fine-grained quantization. So let's come to understanding this right now. Okay, so if you look at the fine-grained quantization section in DeepSeek, you'll see that they have these figure 7 and figure 7a and figure 7b. Just looking at these figures, it's really very difficult to understand what's going on. There are usage of so many colors here. There is something called tensor core, CUDA cores, GEM, WGMMA, scaling factors. So many things are going on. The first thing to understand is that this figure actually consists of two figures. There is fine grained quantization and there is increasing accumulation precision. First, we'll understand fine grained quantization, which is the figure on the left hand side. So, to understand this, the most important thing to understand is this conversion which we saw. So if you want to go from, let's say, floating point 32 to integer 8, what we do is that if you take the sequence of numbers, you divide with the highest number, and then what you do is that you multiply it with 127 because we are converting it to integer 8. So the important thing to remember is that we divide the original number or the original sequence of numbers with the highest absolute value, and that's where we start fine grained quantization. So, for example, if you see, fine grained quantization starts with the scaling solution. So, you have the initial sequence of numbers. What you do is that you take the maximum value of these numbers and then you multiply it with the, if you are converting it to floating point 8, you multiply it by 127 over here. So, if you have this sequence of numbers 2, 3, and 4, and if you want to convert it into floating point 8, what you do is that you first divide these by 4 because that's the highest number, and then you multiply it by 127, and that's how you get the conversion into floating point 8. The reason this is done is that when we move to lower precision formats like floating point 8, we have fewer exponent bits. Thus, the numerical range which we can represent is small, and that can lead to overflow problems or underflow. So, overflow is when the numbers become too large, underflow is when the numbers become too small, and we lose the precision. So that's why the scaling solution is employed, because we can scale the entire tensor based on its largest absolute value. And scaling, just like normalization in deep learning, it reduces this underflow or overflow issues. So this method is very frequently used to convert a sequence of numbers into floating point 8, floating point 16, etc. Essentially to quantize a sequence of numbers. But this approach has a big weakness. The major weakness of this approach is that even a single outlier can drastically reduce the representation accuracy of a whole tensor. And let me explain to you what I mean by this. First, if you take the look without outlier, 2, 3, and 4, we divide all these elements with 4 and then we multiply it with 127. So this is my quantized tensor now, 63.5, 95.25, and 127. And dequantization becomes much easier, right? Then I just multiply it with 4 by 127. For quantization, I multiply it with 127 by 4. For dequantization, I multiply with 4 divided by 127. And I recover back the same tensor which I had before, which means I do not lose any precision. But now consider the case when we have an outlier over here. If we have an outlier which is way larger than the other numbers, then what do? We divide these numbers with 500 and then we multiply with 127. So the scale tensor actually now looks like this. But remember, we are quantizing to floating point 8, right? So there is limited precision. I cannot represent 0.508 as a floating point 8. I cannot represent 0.762 as a floating point 8. 1.016 I cannot represent as a floating point 8. So these numbers, when you actually quantize them, they become like this. So 0.508 loses its precision and it becomes zero point 0.5. 0.762 loses its precision and it becomes 0.75. 1.016 loses its precision and becomes 1. So the quantized tensor loses its precision. And when you dequantize back, you get numbers uh, which are different from the original set of numbers, right? and this is because the quantized version has lost its precision. This is the main issue with having outliers. So in the current approach which we are doing, we take all of the values and then we divide it by the largest possible value, right? That leads to this major issue that smaller values can significantly lose precision. So 2, 3, and 4 are much smaller compared to 500, right? So when you divide all of these by 500 and then you multiply it with 127, you cannot represent 0.508, 0.762, 1.016 as floating point 0.8. So you have to represent them as zero point 0.5, 0.751. So they lose their precision. And when we dequantize back, we get numbers which are not the same as the original numbers. That might affect the accuracy when I train my large language model. Ideally, I want my dequantized numbers to be as same as the quantized numbers. So what's the solution for this? The solution for this is something which DeepSeek implemented in their paper, which is called fine-grained quantization. So if you take a look at section number 3.3.2, they have this subsection called fine-grained quantization, and the first figure on the left is with respect to the same thing. So what they are doing here is that instead of scaling all the numbers by one single number, we break down the entire activation outputs into chunks. So let me tell you what this means. When you are dealing with large language models, we typically have vectors, right? Let's say this is a token for the input embedding token can be a 256 dimensional vector. Earlier, what was done is that we took this 256 dimensional vector, we looked at all the values, and then we found the maximum value and then we scaled all these numbers by the maximum value and let's say multiplied it with 128, etc. Right? That's the approach which I mentioned over here. But now what fine grained quantization means is that you divide this vector into chunks. The first chunk is of 128 values, the second chunk is of 128 values. So this first chunk or this first group is scaled by the maximum value only in that group. So in this group, the maximum value is 20, right? So the first group will be scaled by 20, and the second group is scaled by the maximum value only in that group. So if you look at the second group now, the maximum value is zero point 0.1. So the second group is scaled by zero point 0.1. So we have separate scaling factors. That's the most important thing to understand. If you had a common scaling factor all of these numbers would be scaled by that factor, right? So the second group would be scaled by 20 unnecessarily. That would cause these smaller numbers to lose their precision. But now this second group is not scaled by 20 because 20 is the largest number in the first group. The second group does not care about that at all. The second group only looks at the largest number within that group. So it's scaled by zero point 0.1. So we retain the precision in the second group. So the separate scaling retains the accuracy and the precision for the second group despite a larger outlier in the first group. That's the main advantage which is given by a separate scaling, and that's why it's called fine grained quantization. Why fine grained? Because we are dividing the input vector into chunks. Now we also have weight matrices, right? Several operations in the entire transformer architecture has weights, such as there are trainable weight matrices for queries, keys, values, etc. So many weight matrices are there. So if we have a weight matrix which is 256, 256, we'll divide it into chunks of 128 by 128. So there will be four chunks of 128, 128, and then each of these chunks will have their separate scaling factors. So the first chunk matrix, which is W11, will have a separate scaling factor. The second chunk W12 will have a separate scaling factor. The third chunk W21 will have a separate scaling factor, and the fourth chunk W22 will have a separate scaling factor. So each block W11, W12, W21, W22 is scaled individually. So if W11, let's say, has an outlier, it won't affect W12, W222, and W21. Those will be unaffected by that outlier, which is good for us. So if W11 has an outlier, only W11 scaling is affected, while W12, W21, and W22 remain precise. Their precision is not lost. So fine grained quantization, the name seems difficult, but it's actually very simple. You take the vector or you take the matrix, you break it down into chunks, and you have a separate scaling factor for each chunk. So now actually we can understand what is going on here. So if you see this part is actually the different scaling factors. So here we have the inputs and the weights, right? So remember I told you we have inputs multiplied by weights, y equal to w times x. So this x is what is called as an input over here. This is the first case which I told you, the activation outputs, that they are calling as inputs in the figure, because this is a vector and the vector will be multiplied by weights, which is a matrix. So this is the input and this is my weights, right? So if this is my input vector, which is shown by the green color right now, actually, let me take a screenshot of this and bring it to the whiteboard so that I can explain it to you clearly. So this is my input vector right now, which is exactly what I showed over here. And what they have shown with these different shades of green is the different chunks. So NC, I think, is 128. We break it down into chunks of 128, and then every chunk has a different scaling factor that's shown with these different shades of blue. So every chunk has a different scaling factor. That's what's meant by this first part of the figure, which I showed you over here. Now, the second part of the figure, which is over here, is corresponding to the weights. Now, this figure I believe could have been a bit better because they could have directly shown a matrix over here. But what they are trying to show over here is that we have the weight matrices, right? And those are also broken down into separate chunks. So these weight matrices are broken down into chunks of 128 by 128. That's what's shown over here. It's these chunks. And each of these chunks also have a separate scaling factor, which is shown by the shades of purple color over here. So that's the second schematic, and then we also have this tensor core and the CUDA core over here. So that I have explained over here. So if you look at the tensor core, the green, it's a green rectangle multiplied by yellow, right? So that's actually y is equal to, or this is equal to w x times this is x times w. These are the activations and these are the weights, and we have the output over here. So GEM, when you read the paper, you will see terminologies like GEM. So this is General Matrix Multiplier. These computations happen inside NVIDIA Tensor cores. That's why it's called Tensor core over here. It's not a CUDA computation or not a GPU computation. When you want to there are upscaling factors, right? Because until now what we are doing here is that these multiplications happen in lower precision, as we have seen before. The multiplications, especially if you look in the forward pass, this multiplication happens in floating point 8 multiplied by floating point 8. So this is lower precision. Lower precision operations are all computed on the tensor core. But then once we get the lower precision matrix, we are going to upscale it by dequantizing it and by multiplying it with the upscaling factor. So we need to bring it back to a higher precision, right? Uh, for example, if you take a look at um, the master weights or these if you look at, yeah, the partial derivative of loss with respect to w, it's floating point 8 multiplied by floating point 8, but the product we need to take to a higher precision, that is done on the CUDA core. So this second schematic is the output is stored on the CUDA core where there are scaling factors. So the output from the tensor cores, which is floating point 8, the output from the tensor cores is floating point 8, that is scaled back up to floating point 32 for stability. So here element-wise scaling up or upscaling operation is performed on the CUDA core. That's why there are these, if you take a look at this schematic, there is the tensor core over here where the floating point 8 operations are performed and the result is also floating point 8. And the output is CUDA core where we do upscaling and store as floating point 32. So this entire schematic over here actually has a lot of things which are going on. If I take a screenshot of this and bring it over here, and without understanding quantization, it's very difficult to understand this schematic. So here they are showing the different scaling factors for the inputs or the activations. Here there are different scaling factors for the weights. That's the fine grained quantization part. Here we have the tensor core calculations which are floating point 8, and here we have the output calculations which are on the CUDA core. Those are higher precision floating point 32 computations. So there are actually four parts to this one schematic. That's why reading this paper is so tough, because every single aspect can be broken down into multiple aspects, and that's why this series right now has become almost quite long. But to reach these 16 pages, it's important for us to dive into the very basics if we want to build DeepSeek from scratch. So in this lecture, I plan to cover only this much, where we have fine-grained quantization, and in the first part of the lecture, we covered mixed precision framework. In the next lecture, I'll cover three other things: increasing accumulation precision, Mantissa over exponents, and online quantization. You will see that all these three things come after the fine grained quantization. So after fine grained quantization, we have increasing accumulation precision, then we have Mantissa over exponents, and then finally we have online quantization. And then the whole FP8 quantization part of DeepSeek will be finished. So thanks everyone. We are now going deeper and deeper and deeper into DeepSeek. I don't believe, or I believe this thing which I'm teaching right now is not covered anywhere else, because we are going into the very basics of exactly what these schematics mean. And my goal is to try to explain this to you in as much detail as possible without leaving out anything. That's why yesterday's lecture I had on the intro to quantization, and today we covered mixed precision framework and fine grained quantization. Quantization is extremely important when you are developing foundational models and when you want to reduce the memory requirements, increasing computational speed, etc. So these lectures will be very helpful to you if you are looking to build your own foundational model, which I highly encourage you to do so if you have reached this part in the series. So we have, until now we have covered latent attention, mixture of experts, multi-token prediction, and now we are almost at the end of covering quantization. Thanks everyone, and I look forward to seeing you in the next lecture.